So the idea is we're going to create a program that will print a large number of factorial. Basically, the idea is, how factorial works: 1 into 2 into 3. Let's say we want to create a factorial of 5. Then how we're going to do is factorial of 5. Let's say integer factorial of 5. The idea is it's going to be 1 to 2 into 3 into 4 into 5, right? That's how we do the factorial, right? But if the number is extremely large, let's say we are going to create a factorial of 1 million, or this amount. This requires a huge calculation. The amount of multiplication required for this is huge. And how we're going to do it? Well, the integer definitely would not be able to hold this number. It's going to be huge, large number, right? And integer has a limit of 32 bits, and in 32 bits we can hold only a few billions of numbers, right? That's all we can do. So there is a special class in Java which is called big integer, and we can sort of hold enormous number. It can now let's say okay, so the idea is 1 into 2 into 3 into 4, and it's going to like 10 millions or 1 millions, right? But we cannot sort of write like the way we did over here. I mean, it's not possible by hand. So that's why we do smart things. As a programmer, we can use loop. Okay, so Java 8 comes up with a special iteration process called int stream. Let's create a stream, and we're going to use range closed. We're going to start from 1, because if we start from 0, then whole multiplication will become 0. So there is no point, right? So we'll start from 1, and then let's say we're going to create a large number. It could be anything. The purpose of this demonstration is to show how large the number could be. So the idea is we're going to convert this number to a special class which is called a big integer, so that we can multiply. And okay, so there is a method called map to object, and we can convert it like that. So the map to object, this one is basically going to convert this integer into a big integer so that we can multiply, right? Okay, so we can basically do method reference over here, but let's not focus on that right now. And there is a function called reduce, which is going to accumulate the number. I mean, what we are going to do is we are going to have an expression like this: 1 into 2 into 3 into 4, right? So basically what we can do is we can calculate this 1 into 2 first, and then we can multiply the result with 3, and then the same way we can multiply the result of 1 into 2 into 3 into 4, right? So that's reduce function is going to do that. So we're going to first provide the identity, which is going to be 1. So big integer 1, which is the first value, and we're going to multiply the first value with the two other number. I mean, the reduce function is basically going to get two numbers. So it could be like we can provide a functional lambda expression like this: a into b, and the result is going to be so it's going to be b, sorry. So result is going to be a multiply b, and we can return this, and this is how it's so this reduce function is basically going to represent this one basically. So first one, and then 1 into going to be the next one, the result of the first part, the result of the first multiplication is going to multiply with the second. So this is how it going to work. and the result we can definitely hold this result into a big integer, which is our factorial of 1 million. And let me fix the spelling. Okay, if you are going to print this, you will see this is a really huge number. Okay, let's print it. Factorial of 100 million. You are going to be amazed. I mean, how large this number could be. I mean, okay, so let's print it over here. It's the calculating. It takes a while. I mean, it's huge number. It's coming up. It takes a while. How about we don't do 1 million, because it's going to take a lot of time. Let's reduce the let's make it 100,000, so that it takes less time, and the result is going to be similar. I mean, it's also going to be a large number. Okay, as you can see, it's done, and the number is extremely enormous.
Wow.
Okay, so I mean, it's a huge number, right? And there is no point actually. We don't even know what is the number it is. I mean, it's extremely large. Let's print the bit count, so that we will be able to know how many bit it requires to hold this number. That way, we'll be able to some sort of visualize, basically. I mean, this is the number of bits it's required to hold this enormous number. I mean, for example, if we want to print the how many, let's say we have a integer max. I mean, integer max value. This is the largest number we could hold. We can hold into an integer, and let's see what is the bit number of this max. How about we convert it in a big integer value of max value. Now count the bit count. That way we'll be able to get the number of bit it requires to hold this integer. And it's not going to be a large one, definitely. So it's 31, right? I mean, so to hold a maximum value of integer, it requires a 31 bit. And now compare these two, and now you will be able to sort of differentiate how large the number is. So I'm not interested in this. Basically, I'm more interested in how much time it requires to calculate this whole number, right? So what we're going to do is we're going to remove this one over here, and let's say we're not going to let's keep the bit count, and we're going to move this code into a method. Let's say test, and we're going to run it, run a for loop. I mean, we're going to run this calculation for 10 times, so that the program gets warmed up, and we will be able to get a perfect. I mean, how much time it actually requires. We'll be able to. And now we're going to run this program for 10 times. I'm going to remove this one and see how much time it actually requires to calculate this number. So we're going to, the first one took around 5 seconds first time, and it's getting reduced. The first one take around 5 seconds, then 4, then 3 seconds, then 3.5 second, 3.5 second. Let's see, 3.3 second, 3.13 second. It's around the 3.5 second, basically 3.5 second. That's all it takes basically to calculate this enormous multiplication. Now what we're going to do is we're going to change a little, I mean, this number. this multiplication process. So we did this in a one thread, right? I mean, it's a serial execution, and we have only one thread to do this calculation. If we just run it to parallel, let's see how it happens. What happens? So what we did is basically I have a 6 core in this machine. So what it does is it runs this number into the multiple core. It's only 6. So now if you see the number basically drastically reduced. It takes only 500 millisecond, and then it reduced to 194 millisecond. It's a huge gain. The now question is, how come? I mean, it took basically first time when we were going to do it with one thread. We were doing it one thread. It took like 3.5 seconds, and now it's reduced to 194 millisecond. It's a huge gain. The question is, what did we do extra to get this? To get this 2 number, right? I mean, it's a huge gain in terms of the time. Yeah, definitely. So the question would be, what did we do to get to this number? So the idea is sometimes people would think that because of it's doing in parallel, it's running in six core, so that's why the number is reduced. The idea, this thought process is sort of in a some way accurate, but not entirely. I mean, yeah, we get some benefits from the parallel processing, but then again, if we run a program into the multiple thread, what we need to do is we need to split the programs into, and then we again we have to accumulate. There are lots of overhead of doing it. So and we have only one. We have only 1,000 numbers, right? So we are probably in splitting this number into a lot of into different threads, and then accumulating it. It has definitely some overhead. So this in this program, the parallel actually doesn't do a lot. I mean, it doesn't. It has nothing to do with parallel to get to this reduced time. The actual thing, let's find out what it actually made it faster. If you want to go to these multiply methods, the implementation of multiplication of big integer, you would see that there are different implementation. For example, if it is the number is the both number, the multiplication number is smaller, it's to this normal multiplication. But if it becomes a larger, there are several other multiplication. For example, the one is Suba and the other one is Tim Cook. So the idea is, if the 2 number is large enough, then they do the multiplication with different different algorithm. So it in a way it's a strategy. Basically, if the 2 number is large enough, they multiply in different algorithm, and these algorithm actually way more faster than the normal multiplication process, so we usually do, right? So that's why when we did the parallel processing, basically we split number into multiple processor, and the over here, when we are doing the multiplication into single thread, we are always multiplying the large number with a smaller number. It's been the always case, because the first 2 multiplication, we were multiplying the previous multiplication with a smaller number, and the multiplication become large, and the next number also not a large number, because we have 10,000 number, right? But when we are actually doing it in a parallel, we have a sort of multiplication with a large number, because end of the day, we're going to accumulate the result, right? The result also gets multiplied by the other large number. And if we do this test with normal, for example, recursion, I would probably get the same result. Let's see if we can do that with the in recursion. So we're going to do the recursion over here. Let's write a method, big integer factorial, and we're going to we're going to do the recursion. I'm not going to explain these, but it's a simple. I guess you will be able to understand by just seeing the code. So if recursion has a end. I mean the way to break the recursion, right? So this is what it is. Return, and it's going to return a big integer. I'm not going to explain this, rather let's find the the midpoint. There is an easy way to find the midpoint, which is from plus 2 and then okay, so this will find the midpoint. And what we're going to do is we're going to do the recursion, which is factorial from to mid, and then we are going to multiply 2 mid plus 1 to 2. So yeah, okay, sorry. So the idea is we're going to multiply with another factorial, right? So this is our recursion, the same thing with the recursion, and we're going to test it the same way. So first, let's see. We're going to run this in 10 times, and I'm going to remove this one from over here, and we're going to call the recursion method factorial from 1 to so 1,000 100,000. Let's make it inclusive, close and close, so that I mean yeah. So we're going to run this program, and let's see how much time it takes. So this is one actually doing in a single thread, right? And you can see the number is quite low, right? It's the minimum number it took is 175 millisecond, which is interesting. So what we understood from this program is the multiplication has nothing to do with thread. It has rather than having the advanced algorithm, which is I just displayed over here, which is it has a different way of doing multiplication when the number is large. And the you can ask me why we are not actually doing the we're not using the advanced algorithm always. I mean, we could do that, right? But the problem is there is a setup cost. If the multiplication is simple and we're going to do this, for example, Tim Cook has a different way of doing. It has a setup cost, it has a memory requirement and other things, and we definitely don't want to do or have this setup cost for a simple simple multiplication.
It's Tim Cook, not check করো
Okay.
আরে লাগে শোনো আমার কাছে কিছু
Yeah, there are several algorithms you can look into. The first one is Tom Cook, sorry, the Kaltsuba over here, and you will be able to. There is a link over here, right? You can go to the wiki page and call Kaltsuba algorithm, and there is another one which is called Tom Cook. And so yeah, you can just see and find out how this algorithm is implemented. The purpose of this short video is not to discuss about this algorithm, rather than to find out ways sometimes we can achieve faster result with a smart algorithm. It's not always wise to do the parallel. I mean, if this number was way large, like if it was like a few millions or a billions, then probably the parallel would get some benefits for this particular situation. But yeah, there would be there are always some benefits having parallel, but we should not always aim for the parallel processing. Rather than we should always first try with the single threaded, and most of the cases our problem it could be solved by simple just single threaded way. So yeah, that's the purpose of this demonstration. Thank you, everyone.